All right. Welcome, week 7. Starting to move here. So today we're going to talk about problems and issues with the SIMD stuff. Then we'll get into the file system, and then doing some advanced techniques of the file system. And then we're going to go into sorting and some algorithms. And our basics will be about virtual tables. So I open the floor. Any questions, any problems people are having with SIMD?
I guess not really a problem, more so just a question about how to implement. Because the row major and column major, the last two I'm kind of looking at. And I know I keep forgetting which one's what, because I know like one of them starts with a vector, the other one ends. Like I keep forgetting.
Well, it doesn't, the mechanics doesn't matter, right?
Right.
So it's matrix multiplies, right? So
yeah.
So let's go through some of this stuff and see if this will help. So we have vector times matrix times matrix times matrix, right? Right. And so what you really need to have down, so vector times a matrix is the most important thing. So this has to be really fast. We also have a matrix times a vector, and we need to make sure that these two guys are really fast, right? And so these first two, I think, are the most critical. If you can't get this fast, the chances of getting the whole equation fast is pretty much 0, right? But what's interesting is if you can do a vector times vector times a matrix fast, then a matrix A times a matrix B is done for you. It's actually done. And I'll explain how this is the key guy. Oops. And from my perspective, that this is the key one. If you can do this fast, you get this for free, right? So what is fast? Let's make sure we're on the same page and what we consider fast is. So these are not easy goals to reach. Right? They're totally not, they're not like chip shot easy ones to reach. They take a little bit of effort to get there. But here's vector times matrix, right? And see, vector times matrix is getting 2 seconds, and matrix times vector is getting 2 seconds. Does anybody has anybody gotten results where this guy's slower? I mean, sorry, this one's slower. They should be the roughly the same speed.
I believe I got mine somewhat slower, but I can't remember. I just have to see. Okay. I have to go back, and I have mine working, but I need to go back and make it faster. That's basically
right. So this is one of those assignments where getting it working really doesn't count. It has to get it working in fast, right? Because we can just write it in C++ and get it working. And so is anybody using transpose for this? So let's look at vector times matrix, right? So we have this X, Y, Z, W times the matrix from 0 and 1. And these actually, this is V0, V1, V2, So it's different ways to access the matrix. If you remember that matrix, this vector times matrix. So the matrix is also accessible with the union same as row vectors, 0, v1, v2, v3, right? So that's what these horizontals are, right? So what we want to do is let's do this math by hand. What we would like to do is this, remember, across and down. So it'd be across, right? And then down. I hate this. If somebody understands OneNote better than I do, please tell me. But my problem is I want a square highlighter, and it's horizontally this way, but vertically it's very narrow. And if somebody knows how to make it square or easier way to draw a vertical line, let me know. No, somebody knows a trick, and I haven't figured it out. All right, so you go across and down, then again across and down, right? Across and down. And then across and up, right? Well, this is pretty horrible when we look at this. And the reason why it's horrible is our data happens to be horribly aligned. So when we look at the data, we really want to do our first one is our first entry, you know, because remember this is a 1/4. This is a 4/4. So we're going to get a 1/4 out. So our x component should be x x, y, z, w, m0, m4, m8, and m12. Right. The problem here is life would have been really nice if we had x, y, z, w times a vector, you know, another ax, ay, az, and aw, right? Because then we can just multiply these things together, and boom, that answer comes very easily because we just use multiply. Problem is we don't get that. So let's so this answer, like out of hand, is problematic. Let me duplicate this. So let's do the math here and kind of see what the data will look like. Okay, let's scroll down. All right, so our x component is going to be all right, so it's going to be x times m0. Color have I not used? Okay. I'm trying to get some colors so we can start seeing a pattern. R, X, Y, Z, W, right? And this is M0, M4, M8, M12. And now we go after the Y component. M1, M5, M9, 13. There's a reason to this madness. So this is the answer, right? And there's basically plus signs all across this, right? So there's all these pluses. Right. And what I'm going to do is I'm going to just ignore the pluses after I did all that effort to draw them, because it makes it easier for us to see the pattern. Right. So well, if we sit there and look at this, here's your x's, right? Here's your y's. Here's your z's. Here's your w's. So when I was saying before that this assignment is really pattern finding, and it's a puzzle. You've got certain rules, and what's the puzzle to solve this? So that's interesting. Now we look at this one right here. Look at the m going down this, right? And it turns out M0, M1, M2, M3, this is V0. This is V1. This is V2. It's V3. So now this becomes much more interesting. Like, wait a second here. Again, there's implied pluses here. Right. So here's the green. Okay. So a lot of times in math, and I'll click in here. You always kind of do like, let's suppose we have this a solution and go from there. Let's just suppose we have a vector, right? And its name is x. And this thing equals x, 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 right? We'll call it, let's call it x, right? And no, we'll call it temp t, right? So let's suppose we have this, right? Well, now if we just want to focus on the first column here, we would get this. We would just say underscore m multiply ps, and we'll do matrix dot vo, right, comma time or temp, right? And that's going to get us essentially, that's going to give us this combo right here. And then let's kind of keep our dream going a little further. understand how this rolls. Then let's say we have another temp, which is Y. Temp X, temp Y. Then the next one would be matrix dot V1 times temp Y. Right. And that's going to give us all here in green. Right. And likewise, so this turns out to be green. Oops. Right, so this becomes A, B, and then you see the pattern. Right, and we have M.V1, 2, M.V3, TZ, and TW. Right. So if we do those, we then have this. Right. So now, here's our new problem. How do we add a red column to a green column? So this is all pink or red, and this is all green. How do we add those two together? What function would we call to add those together? See, now this guy here is, this is A, this is B, this is C, this is D. How do we add A and B together? We just call the add function. So now it just becomes and this is your final answer. Is this making sense? I don't know if people are following.
Hey, sorry. So that final answer is what shape?
It's XYZ W.
It's the vector XYZW. Okay.
Yeah. Which is right here. Does everybody follow this or no?
So would this basically be the same thing then if it was like a vector times a matrix times a vector?
Not even close.
Oh.
So has people been coding on SIMD? Because normally I'm swamped in office hours and I got like nobody. So now and the questions right now doesn't tell me that you've been banging your heads against the wall on this.
I've worked with SIMD before.
Okay. Are you so I'm curious with other people, one person worked with it, that's generally rare, but other people, what's giving you trouble with this?
I think it's more so doing the matrix math in the actual SIMD code itself. And just like
the-
working around how to do that in SIMD. Because the SIMD, once you research, like, and just type in like, hey, I can't, maybe I want to multiply, maybe I want to subtract. The Intel site's really nice for finding out how they work.
Well, actually, you have everything. So kind of like to use Wizard of Oz, Dorothy, you had the solution all along. Here's the solution right here, right? You're gonna do the work here, vector times matrix. Boom, right? Go up here to, and I said it was in C. Go up here and it's like, okay, vector times matrix. Vector times matrix. There's the answer.
Oh,
Yeah, I showed that last week. There you go. So there's your, no, there's no math issue now. And now you just got to SIMD this.
Hey, so I'm not deep enough into it to know if I've got questions. I think I can see how the SIMD operations map up to the math that you've got there. I'm just not sure whether the things that seem sort of straightforward to me will perform adequately.
Well, the catch here is there's like, to get this to work, you kind of earned every line of code of making sure you're doing it right. All right, I guess, has everybody done the triangle? SIMD?
Yeah, I mean, you do triangle, but yeah, trying to understand the other stuff and kind of get a pattern is, yeah, it's been something, I guess.
I have the triangle in Sandbox, and I need to
Mhm.
just get it back into the proper test.
Yeah, but do you understand all the things? Because that's really,
Yeah.
that's just programming it. So, so what I'm sensing here, a lot of people, with the exception of Alex, who's done SIMD before, aren't too far along in this. Has anybody, what problems you're having? Well, are people getting the times? I don't think a lot of people have done enough to do this.
That's my only issue is like my vector matrix. Like I said, mine's working, just not fast. So there's like a portion I know I need to fix. And
Okay, so how did you do yours?
the way I have mine, which is definitely such a bad way to do it, it's literally going through and setting, if I'm looking at it correctly.
Is it checked in? Want to do code review really quickly?
Yeah, yes, it is checked in. So go ahead.
Oh.
That's totally fine.
Cool. All right, let's do that.
I will be the guinea pig today.
Well, it's somebody needs to. It's
That's fine.
Yeah.
Yeah.
Thank you. Well, the rest of the class thanks you, and they don't even know they're going to thank you because we need something to kind of get our feet wet, right?
Yeah, that's totally fine. Like the way I'm looking at it is the first half of my vector matrix is definitely not right. And in terms of speed, the second half in terms of implementation, it makes sense.
No, this is PA6, right? Yeah, that's PA6. All right, cool. Let me. So just a word of warning to the class. Do not let off the throttle right now. You should be doubling down because we're getting close to the finish line here. So, hang in there 3 more weeks. You can screw off and play around in the summer, but you don't want to lighten up now. All right, so here we go. So which one do you want to look at? Vector times matrix or which one?
Yeah, the vector matrix one, because
Okay,
that was
this is
my
that one.
speed is not where I would like it to be.
Right. All right. So let's take a look. Yeah. See, you went right back to C. So
Right.
you essentially created this, right?
Yeah,
So-
like these parts is that the first half of like setting row one, like M0 through M15. That's the part that's not right for me.
Yeah,
But,
this one right here is going to bring it to its knees.
Yeah, it's down to like 0.5. And at this growth.
Yeah. No, this is you essentially
But-
undoing SIMD, right?
Yeah, but then the second half at the bottom is what I'm understanding is more correct in how to do it.
Yes, but my point, what I'm trying to get at is, so what you did is this, you basically said, I'm understanding your code, is that here's the code, here's the matrix. I'm going to show you the math part of it. And these are row vectors. And you're like, but I really wanted column vectors here, right? You really want it vertically down. So you're like, oh no, I don't have this. So we'll call this A. So you're just going to create a dot X equals M0. A dot Y equals M4, right? A dot Z equals M8. A dot 3, 4, yeah. W equals M12, right? So you said, create A, and you have your vector here. This is V. Then you just do V times A equals temp1. And then you have created B, you created C, you created D, right? So you have this. Right. And then once you have this, you did a horizontal add, and you said T equals T1, T2, right? And then T equals T comma T3, T equals T comma T4, right? And here's your answer. And this is horizontal add. Right? Is that kind of what you did?
Yeah, that's basically the gist of it, of like making the 4
Mhm.
like that, and then combining 2 and 2, and then taking those final 2
Right.
together, and then getting your answer. That's
right. So
the second round.
so here's your construction of A. Here's your construction of B. Here's your construction of C. You call it row 3, but here's your construction of D. There's your 4 multiplies, and then here's your 4 adds. I mean 3 adds. So okay, so that's what's going on. What's costly to you is is this amount of goo up here, right? This is costing you a lot of cycles. So another way to do this is what if we did this? This is V0, V1, V2, V3. This still doesn't work, right? So another approach is to transpose. And when you call the transpose function, you get this. V0, V1, V2, V3. Now, guess what? This looks a lot better, right? Now it just becomes vector times matrix V0, vector times matrix V1, vector times matrix V2, vector times matrix V3, and then you do the horizontal add. Right. So that's what you did. And if you use a transpose, yours will go a little bit faster. So My guess is what this is like 2 times slower, right? You're getting a ratio of like 0.5.
Yeah, it's getting about a 0.5. So what you're saying then is like from the row 1.x down to like row, like I'm in my code of those 4 sets of 4 that I have, I replace all of that with a transpose.
Yeah. So this right here will speed this up,
Right,
right? You're still paying for your constructor,
of course.
right? But do you really need to have a default constructor?
Right.
So here it's like, so it's set to default, so you're okay with that. All right. So now you do this, you're like, woohoo, now I'm at. So kind of go with this. We'll kind of like go with the first approach. Number one, it's make A, B, C, D by elements, and your ratio is 0.5. Number two, use transpose. It still creates A, B, C, D, but it's a faster way to do it. And your ratio now is 1.0x, right? And then three, is there a way that we don't need to transpose in the first place, right? And so the technique that I just described is called partial sum. You can look this up. I just made up this word, so you're not going to find it. And what it says here is, here's my answer: X, Y, Z, W. So this is the answer, right? But what we'll do is we'll figure out this A component, then we'll figure out a B component, and we'll figure out a C component, and we'll figure out a D component, and then we'll add these together. And so you never get the answer, you never get X until the whole program is done, because you have to get all A done, all B done, all C done, all D done, then they have to be added together before you even get a valid X. But our first pass is we basically fill in A. Then we create and fill in B. Then we add these together, right? We fill in C. We add the result together. Then we fill in D. We add the result together. Now we're at the answer. And there's no transpose at all in this environment. But what we did was we kind of shuffled the problem around. Right. We have this. Create a temporary vector X. Right. And then we're going to do some right. Then we're going to create another temporary Y. Right. And might as well finish it off at this point. TZ. And then these ones will give us A, B, C, and D. So now we have this. A, B, C, D, right? Then when we want the answer, it's, A plus B equals temp. And then we have C plus D equals temp 2. And then we have answer equals T1 plus T2. Right? So we know how to do all this, right? So we know how to do all these. Right? We know how to do this one. Right? So the real question is, how do we find that guy? Right? It's just a puzzle. And so here, this one says, give a float. It's going to write the answer. Whoa, Nilly. Given a float A has 32 bits, right? So it's one float. It's going to be written to J, which is 0. So this is going to be 0. So it's going to be written to 0 through 31. So this is to X. Then it's going to go to 1 for J. So 1, so it adds an offset of 1 float. So basically this function here is going to replicate the X 4 times. Or you look at load 1, and this is going to do, given a pointer, replicate it 4 times, right? So a lot of times, this one right here, this function, you can look up, set, and that will create that function. So now we know how to do it, right? And so now we have all this, and this code here isn't that bad. One set, all this stuff. And all we do then is rearrange and reduce for timing. But what's important is there's no transpose. So to go back to here, no transpose. Now we're getting 1.5 ratios. I'm sorry, we're on this one, 1.5. Right. So you kind of see how just coding it doesn't get you there. You have to code it and reduce operations. And so the first approach was the most straightforward approach, but the setup of ABC costs too many cycles. The setup here with the transpose still costs a lot of cycles because we're creating ABC. On the third one, the one I showed you, there's no even ABC. So the cost we added here, the cost, that we added here was basically create an X, 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 which is one function that boom, creates all 4 of those. So this is faster than a transpose, and it's much faster than by element.
Hey, in those 4 X's you have there, Are
Mhm.
those actually the four different X's, or is that X replicated with the, like the set function?
That's
in your-
X, that's four X's. So it will create four XXX. You give one X and repeat it 4 times.
Okay,
So this will actually create, here you give one address and it's going to create 4 copies.
can you go back a sec to how that flows into the solution? I know you had the XXX, YYY, W.
So we have set 1, or it's just a big puzzle, right? So here's one. This one here is you give one float and it's going to replicate it 4 times, right? There's another one you can do is you can literally do set, I think. And you can do this. Now you have to put in X, comma, X, comma, X, comma, X. And my argument is this is pretty close to that first approach we saw, right here, because you're setting it. So, you're not getting not much of a win there if you have to manually copy the variables. So once you figure out how to create this, and you have a couple choices, you have, load, 1, set, 1, and set. So here's a couple choices that will create this, right? And they all have different pros and cons. But then we just sit there and you're just creating this as a line. You just replace it with the word set. Am I answering the question?
Yeah, what you were, so what you're showing now is what the question was, is the 4 W's that you have green highlighted there.
That's the set function.
But those are coming from where? I thought that those were actually the 4 different W's that were partial sums. And
No, these are technically v.w, right? It's the v.w. It's
from the vector that's being
It's right
multiplied
here,
by the
yeah.
matrix.
Yeah,
Got it.
It's v. So v.w is replicated
okay.
4 times. And so you can see here's that w, and then we go down here. Here's the y. This is a v.y, v.y, v.y.
Okay, got it.
So basically you're just saying, let's pretend we have this function. Can I work with the rest of it? And the answer is yes, and this will get you your speed drastic improvement. All right, so now how do you, once you can do this, once you can go v times matrix and it's fast, right? Right? You now have, you can take that code and you can get matrix times matrix, right? Right. So why do I say that? Right, matrix times matrix, right? Again, we can always look at the source code here. Matrix times matrix, here it is. Boom. This first one is vector times matrix. This one is a vector times matrix. This one is a vector times matrix. This is a vector times matrix. So let's take all this. Matrix will be this one here. Matrix times matrix, right? All right. And so what is this line doing here? Well, let's look at the matrix, right? We have this. Okay, so how do we do this? It's going to be across, down, right? Then it's going to be across, down, across, down, across, down, right? So this turns out to be this. As we scroll down here a little bit, you have this vector times matrix, right? This happens to be vector 0. And see, there's all your vector zeros. Then with our magic eraser, across, down, 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 right? That one here is really lose my mouse, there it is. That's really X, Y, Z, W, vector 1 times matrix. So this is the green. This is the pink, right? And you can see green, pink, yeah, blue, right? So essentially, this turns into 4 matrices. I mean, 4 of those, right? So when you see matrix times matrix, what I see is this. I see matrix A, matrix B, right? I see matrix A V dot V0 times matrix B, matrix A V1 times matrix B, matrix A dot V2 times matrix B, matrix A times V3 times matrix B. So if you have a really, really fast vector times matrix, and this is fast, you cut and paste that code 4 times. So to look at, oh, sorry, let me just, so then, so here's this, the reference code. This first line here is literally, matrix, it's this, V0 times, it's T, right? Oh, I got different variables here, but anyway, it's this times your input matrix, M. But you see what I'm saying? So then you take your SIMD code and you go dunk, dunk, and you cut and paste SIMD here, right? Change the variables, do it again. Boom, and SIMD here. And you keep on going. Then you got everything in SIMD, then now rearrange for speed. Does that make sense? Yes, no, maybe so.
When you say rearrange for speed, you mean just to get the resulting vectors into a single matrix to print?
No, rearrange the timing for speed. We'll talk about that now, I guess. All right, so let's play SIMD for a second here. Let's say here, okay. I want to do, let's ignore this function. I just want to have like code here so we can sample and kind of talk about code here. So don't worry about what this function is called, right? Let's want it someplace where we can write some code. All right, so let's give ourselves a pseudo operations here. Let's sit there and say we want to do A times B, right? And that equals plus C times D plus E times F. These are all vectors, right? And we want this whole thing to equal G, right? So these are all vectors, right? So we have vector, A, B, C, D, right, and G. All right, so let's pretend that's what we want to do. So let's code this up, right? So one approach is to literally code it up as you see it, right? So A times B, we go to this and we say, okay, multiply PS. There's multiply, and it's A times B, and it's going to multiply this out, right? So first of all, does everybody understand what I'm trying to write here? Yes, no?
Yeah.
Okay, so we just do this underscore M multiply PS A comma B, right? And then and this will equal some temp T, right? T0, right? And then what we're going to do now is multiply CD together. CD together. And then then what we'll do is we'll sit there and say temp 0 equals temp 0 plus temp 1. Add those together. And then the next thing is it'll be now we need to get E times F. So T1 equals underscore M multiply PS E comma F. And then our last thing is to add those two together. So we have T0 equals add yes T0 comma T1. Right. Will that give me the right answer? So this gives me for T0's that, T1's that. Now T0's this, T1's that. Now T0's the whole thing. right? Does this make sense? Does everybody follow me or no? It's okay if you don't, but please speak up. So here, this is T0 is A times B. T1 equals C times D. T0 equals A times B plus C times D. T1 equals E times F. T0 equals A times B plus C times D plus E times F. Right? So that seems to be working. Does everybody agree with that?
Yeah, that makes sense.
Okay.
Yeah.
So you see, all I did is this, the puzzle and all the two pieces I'm using is multiply and add, right? Pretty easy. All right, so now, remember when I keep saying, do it all in SIMD, then rearrange it, right? Now let's go into rearranging, right? So when you look up multiply, you multiply here, you see this whole thing. You see latency and throughput, right? And latency is not a bad word. Throughput is a horrible word, right? It should be really called, you know, this is the time for one, this is the time for repeat. So single and repeat, right? So let's talk about what those are. So if I had an operation that said multiply, right? Multiply A comma B, right? And that output's going to go into C, right? So let's just go with that. We need to, first of all, look at this and kind of take numbers, right? And what I always do is I just use Skylake, and this is a hardware technology. And I'll just sit there, go 4, and then I'll just round this up to 1. Half cycles is much more complicated. So this is rounded up to 1. So 4 and 1. So latency 4, throughput 1, right? One, 4. Yeah. Throughput. Right. So now what I'm going to do is, you know, cycles. It takes 4 cycles and repeat 1. So I don't like the word latency and throughput. I like the word cycle and repeat, and you'll see why in a second, right? So we do this, right? So here's this line of code. This is number 1, right? Then this is number 2. This is number 3. This is number 4. Right here, 5. C is ready. Put the cycles in the front. So this takes 4 cycles. 1 cycle to multiply it, 2, 3, 4. Now C is ready. So that means now I can use C here, right? So this is really C, oops, C. And this is, it takes 4 cycles for C to be ready, right? So now I can do this right here. Let me not do that. Let me change this for a second, just to kind of show you a little more of this. What if I did something like this, which is pretty easy? A times B times C times D, right? That's my answer. Right, so that's what I want to do, right? And this is how you coded it up. Multiply C times D. And that gives you E, or we'll call temp. And then we get the code right first. E equals multiply temp, comma, E, D. Okay, so here, this is how we'll do this. All right, does this look like right? A times B gives a temp times C times D. So we did this. Boom. Boom. Right. That's how we multiplied it. Right. So now let's look at this from a cycle count. First of all, this code will work. Congratulations. You know, you got code to work. That doesn't mean it's necessarily as fast as it can be. So we look at the cycle and repeat, right? So just for here, let me just give this a numbers. T1, then T2. This way we can differentiate the two T's, right? All right, so T1. So let's put the cycles up here. T1, so we got T1, cycle 1. Now what's going to do, remember how we had alignment in earlier in the quarter? This is padding for cycles. Here's T2. Before. Now T1's ready. So right here at this line, T1's ready, right? So now we can actually use it. Boom. And so now we start the T2 countdown. T2-1. T2. Oops. Dash 2. T2-3. T2-4. And now T2 is ready. Right. So in this line here, T2 is ready. So we had something that looked like it was, so here's our original code. Just really quickly show what the original code is. Right, and it looks like there's 3 cycles, right? No, it's 12 cycles. Right, so can we do better? Right, well, what if we just learned what cycle count means? That's what cycle count means. It says it takes 4 cycles for T1 to be ready. So one cycle, 2 cycle, 3 cycle, 4, it's ready. I can use this line. T2, 1 cycle, 2 cycles, 3 cycles, 4 cycle, T2 is ready. Then TE is ready down here, right? So this takes right now 12 cycles. So now what if we take this and rearrange this and say, you know what? let's change our grouping here and do it this way. Right? Still get the same answer. T1's not running until this line right here, right? It's not ready to there. But we have the repeat, and it says I can repeat every 1 cycle. Cool. That says, when can I use this function? Every 1 cycle. All right. Here's the 1 cycle. So therefore, I can start this here. And I can do C times D, right? But now I have to start my counter for that one. T2 dash 1, T2 dash 2, T2 dash 3, T4, right? But T1's ready at that line. Well, what's the next thing I need to do? You know, we kind of have this. T1, 2. Well, now I just multiply T1 and T2 and I get E, right? Well, that's not ready. You know, T1's ready. This line here, right? We didn't start anything. Now at this line, T2 is ready. Right? So now I can start my multiply. T1 and T2. Right? So now this starts the E series. E dash 1. So do you see kind of like how this works? Is repeat says how frequently can I start the function again? And cycle says how many cycles it counts before it flushes through the whole system. So now if we count the cycles here, we have 4, 5, plus another 4. So now this is 9 cycles. Right? Which is a huge improvement over 12. Right? 25% faster. And all I did is rearrange this. Does this make sense?
Yes.
So the goal here is when you write your code as small as possible in the most efficient math operations, right? So we look at our code here. Here's our code. This is as small as possible, right? Then we're going to rearrange this based off of delays. So now we go into this phase, rearrange by delays. So we look up here, multiply is cycle count 4, repeat 1, right? And then add, I think it's the same, but let's verify it. Add. Yeah, 4, 1. All right, so adds the same. All right, now let's look at our equation here and can we make this better, faster, or whatever, right? So a couple things we realize. If we can keep multiplying if we aren't dependent on the result. So if I move this guy, right? All right, well here, I guess we're going to sit there and we have to first see where we're at right now. Here's T1, T0 dash 1, you know, T0 dash 2, T0 dash 3, T0 dash 4, right? And if we do this here, we can move this guy up here to this line. Right? And then we start a T1 clock, 1 dash 1, T1 dash 2. Oh, I'm sorry. I already started optimizing it. Sorry. Can't turn that bit off. There you go. Right. T1 from 0 dash 4. No, this will, I'm sorry. I was right. I can slide into, there's no restriction. So yeah. Because C and D are not T1 or T0, so there's no delay. We can use the repeat mode, right? So this is T1 dash 1, T1 dash 2, T1 dash 3, T1 dash 4, right? Right now, how far can we move this line of code up here? I have to wait till T0 is done. I have to wait till T1's done. So this is the first line I can do it. Right here. So now this starts another timer. Right? Because we need T1 this to be answered and 0 and 1 done, and that happens below that line. So boom, we can move it here. This starts the clock for this. Where can I do this multiplication here? Right? Right now, it looks at this and goes, hey, wait a minute. I'm on E and F, right? There's, you know, it's not going to rearrange the ordering. So the first slot it can do here is this line right here. You can do E and F there. And now you get this, T1 starts here. We weren't really that inefficient in the first place. Right now, these are all zeros. Right now we can do this, and those two are clear. So it's T0 dash 1. Right. So this is our whole solution, right? So this is going to count 4, 4, 4. So 12, 13, 14. So this is 14 cycles. Our initial pass is 14. Right? Does this make sense?
So are you saying that if we do the A, B, and the CD in our code, the compiler will then start these instructions for us at the first time that the multiplier is available?
No, it's not going to reorder. Right? So now the catch here is, can we make this better? And of course the answer is yes. So this is what we originally wrote. This is just the timing of it, right? So now now let's see if we can improve this, right? So can we improve this code here? Well, we can start this multiply over here, right? And we just call it T2. So we do that. So we start T2 here, and this starts a T2 clock, right? And so what we're doing is basically doing parentheses around each one of these first. Right. And doing that, so now here is T2-2, T2-3, and T2-4. Okay. So this is where we're at right now, right? Now, we would like to add these two guys together, right? That's T, so 0. Right. We like to add T0 and T1 together, and we can do that after this line. Here's, oh man, I've got a weird cut and paste here. 1, 2, 3. This should be 4. 1, 2, 3, and this should be 4. Okay. Yeah. All right. Let's just tighten this up. Okay, so we can add these two after that line, after this line right here, right? So this is where we start. T0 equals underscore add PS T0 comma T1. Right. And now this starts a new clock. Right. Now we added these two together, so we did this. Now we need to do our final add. Plus T2. T2 is ready here. So this is the last one for T2, but now we have to wait till T0 finishes. So it'll be right here. So now this is the first line here. So this would be G equals underscore add PS T0 comma T2. Right. And then this starts the G clock. G-1, G-2, G-3, and G-4. So now let's count how many cycles we got. We have 4, 4, 4, 12, one more 13. So now we're at 13. Right. So not much of a savings. We went from 14 to 13. And it just happens I gave you guys I just made up this problem on the fly. I gave you a problem and we started coding it up in a more efficient way. So, that's bad on me. But we were able to shave one cycle from it. But if you look down here, here's these multiplications, 12 cycles, and rearranging things, we're down to 9 cycles. So this is the last part. Once you multiply everything together, so once you do that whole SIMD goo, where you take the matrix times, all that, you cut and paste that code 4 times, make sure it works, test it. Then you start rearranging it based off of your timing, and you can shave more cycles. Does that make sense? So scarily quiet. Questions, things people aren't understanding, people who aren't talking.
Hey, so there's a question comment on the chat about a trade-off of the number of temps you're making versus arranging the code. Are you actually making more temps this way than you would a different way?
That's the thing, you have to kind of look and see into it. Is this going to give you a net thing? I try to reduce the number of temps because the temps are going to eat cycles. But if you declare your vectors, and we did this, if you declare a vector as default, the compiler sees that there's no need to initialize it. It's just going to write into it. So it costs you no cycles. So a defaulted empty variable shouldn't cost you any cycles. So, but I still wouldn't create too many temps. If you create an explosion of temps, you're going to get yourself in kind of a scenario here where it's going to, you want to basically get your code as efficiently diced in here so that the compiler is almost a direct one-to-one translation. So temps get you in trouble if you are not reconverging, if you leave them all loose and open. So like here, I recycled this, right? So let's look at this right here. I have 3 temps, right? But I'm recycling temp 0. I could have called this temp 4, right? I could have made this all temp 4. And this is temp 4, right? And then this would be 4, right? And I run the risk of, if there's a little bit of overhead on the construction, it may bite me, So I try to keep my variable count as low as I can get away with it, but I'm always going to default of how do I shave cycles here based off of the throughput and the latency. Those will actually give you net benefits. But if you just go explosion and have 15 or 8 temporaries, then you're actually going to probably incur a cost.
So with these intrinsics, are the operands fitting in CPU registers, so they're not really out in either cache or memory?
No,
Or-
these are little micro programs, microassembly groupings. Right.
Yeah, so I was looking at last week's lecture, and you sort of started out talking about the 386 and the 387 coprocessor. So is some of this processor supported? Is all just straight away, plain old memory, and they're just assembler
This
macros?
is just in there, and people just don't use it. It's available. It's there. It's sitting idle most of the time.
So it is processor supported.
Oh, it's built in the processor. Yeah.
Okay.
Yeah, there's a there was a function in the lecture. There's a lecture that the thing that said I think it was ID. right? So there's CPU ID and CPU ID extensions, right? And you can query this on any processor and it tells you what SSE instruction set is supported. So if you try using a function that's supported, it will generate the assembly code. There's assembly code. If you wind up generating code that and your CPU doesn't do it, it will not compile. So it won't emulate this. It's like use these machine code or not, right? So this might tie it home a little better. If we look at, here's wrong button I pushed. So this is row major. Come on, computer, hurry up. There we go. All right. So here's my row major, right? And the reason I'm doing this is just to click this button to show you disassembly. There it is. And so this is just getting ready to the function. Then here it calls my my proxy vmmm, right? Boom. And now my proxy, right? There we go. And here you can see multiply PS, multiply PS, multiply add PS, move PS, add PS, move PS. And if you see all the XMMMs instructions, that's all the SIMD. And this is literally full. So like, you know, a couple of these functions, you know, they're not necessarily one-to-one, they're close. But what you'll see is when it reorders things, you'll see all the MMs, XMMs all next to each other. And that's when it's just going crunch and it's going really fast. So I think your question in trying to understand this right is when you sit there and use underscore multiply PS A comma B, this is going to generate, you know, a couple assemblers with hints. And then this other one here, couple this generates some assembler with hints. And now, because of this hints, the compiler can further rearrange and move the collection up and down in the function.
And will it do that to help so that you can, as long as the operands you need are available, that it'll start on whatever cycle it can start on?
If your system does not support this, it gives you a compiler.
Okay, but if it does, I'm talking about the rearranging, what rearranging it's gonna do, so where you were doing A times B times C times D, and then you change it and said, look, instead of doing A times B times C and then multiplying.
Well, no,
and
it will not. You have to manually rearrange it yourself. It's
Okay.
not gonna, it's not what you're asking, Paul, and if I understand this right, hey, you know, we did this whole rearranging here. Will the compiler do it for us? No. And I'll give you a practical way to prove that, right? Code this up, measure the time. Code this up, measure the time. This one's faster. If the compiler will rearrange it for you, there'd be no speed difference.
Okay.
You know what I'm saying?
Yeah, I have another question,
Mhm.
kind of related. I think I saw either in your lecture or in some of the documentation that there's more than one of these underscore 128 structures available, like maybe 4 of them in some of the CPUs.
Yeah, but that's that's when you're going to the more advanced instructions at the AVX.
Okay.
Yeah. So
And
on here, when you get into these things right here, boom, open this up. Oh, here, or this one, there, boom. This one has 4 128s.
Okay. And then
But that's off limits for this class.
No, I understand. Hopefully we'll be done with this one day,
Yeah.
and do that other stuff. Do you have to multi-thread to get that, or will the
No.
compiler, put 4 things side by side for you?
If you're aligned, everything's predicated if your data is aligned.
Okay.
That's the whole thing, right?
And by aligned, you mean aligned to the width of
Well,
that
to the width of it,
data
right?
structure.
So for
More
us,
flow.
everything has to be aligned to 128.
Okay.
For this 512, you might have to be aligned to 512. That's my gut guess is. But if you're aligned, that's the first precondition. Then you can use these instructions. If you're misaligned, you can't do the instructions because it won't compile it.
And if you're using that underscore M128,
It's guaranteed to be aligned.
it forces it to be aligned. So as long as you
Right,
use
no.
that, you're
Okay,
immediately aligned.
forces it to be aligned. And normally I talk about this next week, but I'll mention it this week because you came up with the question naturally. When you use the underscore M128, right? If you have a function on the stack, this is aligned, right? This is happy, right? We have it inside of a vector, right? With a union. So our vector, that's aligned. Right? The problem comes in if you pass it, right? So let's do vector A, and you pass it in a function A, right? If you pass it by value, so here's your function void foo vector, V, right? This is by value, right? And what they do is on the stack, it passes in a X, a Y, a Z, a W, right? The stack is not guaranteed to be aligned. So if you call a function on a method that's by value, it may work or it may crash. Because we don't know what our stack is. So you always pass, if you're going to pass this to a function, your vector to a function, make sure your function is a pointer, right? So make sure you are a reference or vector star v foo 2. Then you're passing this address into it. And this is guaranteed to be aligned.
Okay.
right? So stack vector A foo vector V foo vector address of V foo vector pointer to V, right? Smiley face, smiley face, frown. If it's on the stack, right? If you sit there and do this, vector star P equals new vector, then you're in screwed land, right? Because this address points to a vector, a x, a y, a z, a w, but the first word here is a float. So this is just guaranteed to be 4 byte line, which may or may not be 16 byte line, right? Just where did your malloc give you? And next week we'll talk about how do you align a vector, a new function, or
And is that if you don't use the underscore?
no, it doesn't matter. As soon as you call
Oh.
new, like right now, when just think about our memory system from PA4, you allocate something. What's the alignment of that? Who knows? It could be 32-bit align, it could be 64-bit align, it could be 4-byte align. You know what I mean? It's just where, what
Yeah.
address did it land on? So when you do a new, there's no alignment guarantees. But we'll talk about that next week when we get into how do you deal with overloading new and delete. But that's, I wanted to show you that when you're dealing with this, because it's on the stack, internally, there's an underscore M128. So this is aligned. So this guy's aligned. Right? Line to 16. And then if you call by value, it may not work because the stack might be misaligned. But by reference or by pointer always works. Next week, when we talk about new, we need to find a way to guarantee that our new is aligned. And that's a bigger mess.
I get one more question on that underscore 128
Mhm.
or M128 guy. In your anonymous
Right.
your struct with the anonymous union in there, you've got X, Y, Z, and W.
Mhm.
If you look inside the underscore M128,
Yeah, it's an alias. Yeah, it's just a different name.
yeah, there's an array of 4 floats in there, and that's
Yeah.
the same thing, right?
Right, but you don't want to access it by an array ever.
Okay.
Right.
Because
So
it's faster, or because it's easier to understand yours?
no,
Yours is
because
definitely
it's
easier to
slower,
understand.
right?
Okay.
So here, you have a class, right? The class here is going to be float A, B, C, D. Right? Class dog, class cat, float, A bracket 4, right? Let's say we want to access the third element, right? So we would do this arrow C, right? We do this arrow A bracket 2, right? Is that correct?
Okay. Yeah.
Right? This instantly, here's your answer. There you go. This is, what does this do? 2 times the size of float plus the address. Dereference it.
Okay.
Never use arrays. Right. I know this is contradictory. What a lot of times they'll say arrays are arrays. Arrays will get you working, but if you want performance, that bracket going in there costs cycles. So even though the M128 internally has a float 32 bracket 4, if I remember right, something like that, right?
Something like that.
If you want to get to the Z element, you can just go underscore M128 dot float 32 bracket 3 2, and you know, or we just go this arrow Z, sorry, Z. Now, compilers can optimize this into that, but they don't guarantee that it's there. And whenever I write code, I'm going with as much as possible stuff that I guarantee will work, as opposed to stuff that I pray to the compiler gods to make it work. An example of this is your code did the right thing, and you add a little more code, and the optimizer didn't optimize it, and it actually made it slower. I've seen that happen. But if you give it no option, it has to choose the right way. All right. We're still reducing temps, but we have another qualifier on it. So Anne was asking, you know, what if we reduce temps? It was better. It's always better to reduce temps, but we have one extra condition, and this is only for SIMD, is we have to look at the timing, right? So temps, right? Algo, right? So here's the order that we kind of go through. Algo is like, can I reduce the multiplications and use the most efficient programs? Then we look at it from timing. Then the last thing is try to reduce the temps. So temps is still a very critical thing, but in SIMD, we have to focus on timing. Otherwise, timing, this is that latency and, you know, repeat. Okay. So there was a couple questions about proxies. Does everybody understand the proxy stuff? It's just we're going to multiply it in the opposite order. So matrix times matrix times matrix times matrix times vector. If we presto changeo these into a proxy, then we just have a structure, and it has M, A, M, B, C, M, D, and vector. And now we can use these in any order. And now we can multiply it, you know, starting here, going that direction to reduce our complexity. So that's all the proxy does. You know, proxy just buys us this. It puts it into a structure, and then we can do any order. All right, get going on your math. This item, it's 10%. It's pretty big, but get your hands dirtier. All right, let's start. I don't, something's wrong right now. There you go. All right. All right, so our next thing we're working on is it's the file system, and the file system slides are simple. I might buzz through them really quickly, but I'd rather kind of talk about the bigger issue here. How do we sort? And for those who haven't seen this material before, how do you sort a linked list? Right, so it's a double linked list. How do you sort it? Anybody? If you haven't seen this lecture, so I'm looking for everybody's new to this question. Not
Sorting,
Mhm.
you asked what algorithm would you
Yeah.
use?
Mhm.
I'd say the start, knowing nothing about it, just a binary search.
It's a linked list. Where's your binary?
Oh. That's a good, yeah, I was thinking of finding, yeah.
Yeah, sorting. They're out of order, right? Anybody? This should have been covered in data structures, right?
I'm thinking.
I mean, I
basic
guess-
traversal.
Excuse me, what did you guys say? Go ahead.
Oh, I was going to say basic traversal and then just switching it up.
What basic what?
Traversal from one point to the end. And
Yeah.
then
So you start from one. Yeah, you're absolutely right. You start from one, but what's the algo do you use?
Is it merge
Bubble
sort?
sort?
Okay, so there's bubble sort. And so let's go down to things bubble. Any other choices? Do you guys know?
Merge?
Merge. Okay.
Insertion.
Insertion. There you go. Right. Quick sort. All right. So quick sort needs an array. So not good, right? So we kind of got the choices here, right? So bubble sort is like if you were gonna, if I put you in a room, I said you have to sort something and your code has to work, otherwise you get fired. You will come up with bubble sort on your own, just naturally. This is a natural algo, right? It's horribly slow, but it will work every time. So if you were gonna bet money, you can probably code up bubble sort cold, right? But turns out these two algos are pretty good for linked lists, right? So here's the catch. A lot of people don't realize this. If we look at insertion sort, its order of complexity, right, is n squared. Merge sort is n log 2 of n. So let's look at this right here. On the surface, I'm going to start with a new one. On the surface here, here's n squared is really easy. Work. It looks like a parabola, right? This is insert. And then here is merge sort. If I want to write this code to be as fast as humanly possible, this is the number of elements, right? And this is time, right? We want to try to keep the time down. Well, you're like instantly going, well, I'll just go with, I'll go with merge sort, because as the numbers get really large, it's going to be shorter on time, so it's a clear winner. And if you look at the textbooks, like all day, they'll tell you merge sort, merge sort, merge sort for linked lists, right? But if you look at this chart and we look at insertion sort, it starts here, and then it goes up, and it just keeps going really fast up this pathway. So what we really want to do is this: do merge sort, but when it hits this threshold, we want to change directions and go insertion sort. And then we're going to get net faster code. So as we're sorting, let's say 500 sub lists at a time, we'll probably be in merge sort land, right? We'll probably live over here. But then we keep taking the 500s, break it down, break it down, break it down, break it down, and get smaller. At a certain point, we're sorting a sub list of 16 elements. And if we're in 16 elements, probably insertion sort is faster because merge sort is slower when the number is small. So we need to kind of keep an idea on these charts and algos. So here's what we're going to do. First, merge sort, insertion. So here's insertion sort. You can kind of see it. So it goes, I look at the next one. Oh, you're out of order. We'll swap. Then I'm going to go to the next one. And then I'm going to insert it where it makes sense. No, not there. Put it in the beginning. Then take this one. I'm now going to grab it and insert it. And all along, the front of the list gets more and more sorted. Right. And here it's like, oh, it's already greater than 6, so don't do anything. So insertion sort is definitely better than bubble. Because you have relative ordering as you are inserting, you can abort earlier, right? So we know it's before 3, so we don't have to check if it's before 0 or 1. And like here's number 4, we can sit there. We know that as soon as we find a spot that fits, anything to the left of it, so 1, 2, and 3 is lower than the 4, right? So we get some algorithmic benefits from insertion sort, but as that number gets big, you can have that worst case scenario where it's like the smallest number is at the end of your million node linked list. You're like, crap. And now you have to walk it all the way back a million. That's where it eventually becomes n squared. All right. So that's insertion sort. And so here's merge sort. Take the list, divide it in half, then keep dividing until you get down to individual elements. Now, take the first 2, group it and sort it. Take the next 2, group it and sort it. And so now these little islands are relatively sorted. And basically the whole thing here is as you merge, now you have still relative ordering, right? So now that sublist of 4 is sorted. And then this sublist gets sorted. Now you have 2 sublists, each are sorted. Then you sort those by merging again. So that's hence the word merge and sorting, right? So one of the things with optimize C++ is not only do we have to be optimal, we always have to be totally aware of algorithms. If we use the wrong algorithm, no matter how cool and clever we are in C++, we can actually lose performance because we're using the wrong technique, right? So this assignment, we're going to be doing the sorting. Okay. And which right, so here we are. So here's debug, and insertion sort here takes 1.7 seconds. We switch it to merge sort, 0.6. Why is this such a big number? We're sorting 400,000 linked list nodes. So it's really large, right? If you stay 100% only on insertion, you're starting getting into the n squared section, right? But because we have 400,000 linked list nodes, you get down to 6. Then I programmatically and experimentally figured out where's my cutoff on my machine. My machine was around 64. So if I sit there and say, if my sublist is less than 64, call insertion sort. If it's greater than 64, stay on merge sort, right? So I do a merge sort algorithm with one extra conditional, which is if my sublist is greater than 64, less than 64, switch to insertion sort, otherwise do this. And what you see is, it's really interesting. If you write the program, most people do not write the program correctly. But if you write, you write the insertion sort, and then you write a merge sort, then you're going to create a new one called combo. And then what you pass into it is n, right? This is your n. And you measure the times. And as you do it, you'll see your times doing, it's kind of like really long times. And it kind of does this. We're looking for what is the n that gives you the kind of the bottom of this, the shortest amount of time. So you experiment on which n to pass in here. So you run it, 20 times and keep changing the number n, and you find out where does it kind of give you the fastest times. And that's your n. What does this n affect? Well, this is your CPU hooking up to your RAM, and then how much L1, L2 cache you have in here, your bus speed, right? So we have access to memory affects that n. How much cache do you have? And is it two-way, three-way, one-way, two-way, four-way associative cache? That affects n. What's your processor speed? Your processor speed can be fast, but then you have a slow bus. So we have, CPU speed, right? So basically everything affects n, right? And so everybody's machine will be different. So, on one person's machine, n is 32. On a different person's machine, n might be 48. On another person's machine, it might be 64. If you find yourself doing, hey, my n is 100 or greater, you didn't do the algorithm right. you screwed something up. You didn't write it correctly. You're not really, you didn't write your combo algorithm right. There's a mistake. So if you're finding your number really large, you didn't write your code right. So my expectation is n is going to be somewhere between 16 to 128. And if you're anywhere outside that range, you more likely did it wrong. My machine's 64, and I built my whole machine with the idea of cache coherency multiple processors. So, and I'm 64. So if anybody is over 100, you better have a machine that is so hot it melts your carpet when you turn it on. Right. So that's the assignment, the first part of the assignment. There's multiple parts, obviously, and you're not alone here. What you're going to do is I'm going to give you reference material. And because, it's not an algos course, you have to start from scratch and do your algorithm. So here's the two. Oops, buddy. Maybe it's fired up. No. There you go. So here is geeks, and basically insertion sort for a single link list. So here's a single link list. Here's the C++ code. And you can start cutting, pasting, and grabbing this. The catch is this is a single link list. So you're gonna have to rework this. And this is good because sometimes it's good to look at somebody else's code and try to understand it and try to refactor it to your style. And you can see in this code, I think we just here, copy. Does this copy? Right. So this is somebody's code. You can take a look at it and kind of grok through it. But there's things in here that are already horrible, like using null, some of the way this person's using this stuff. You'll find some issue with it, but it gives you a starting point. And a node here has just the next pointer. So you're gonna have to refactor that to make it also a double link list. And that's your insertion. And likewise, there's the same link for merge sort. And so here's the C++ code. So you can start from this and refactor it, or if you're crazy enough to start from scratch and try to write your own, go for it. Then you take those two solutions and you're going to create a combo, right? It's not going to be merge calls insertion. You're going to have to rework it so that the insertion is built into it. And you're gonna have to refactor some things to make it there because there's no concept of length of the link list, sub list. You're gonna have to add that code. So you have to add a little bit of work here. And so here's the code. Right, and you're gonna write the insertion sort, the merge sort, and then the combo. And so you're just going to literally do all your work here, merge, all your work in insertion, right? All your work in combo, and it gets passed in the combo. And then what you're going to do is you're going to add the offset. What is your cutoff? So when you're playing around on your machine, you play around with the number and you leave it there. When I run the unit test, I'm going to replace it with the one that's appropriate for the test machine. But you'll see a benefit. You'll see the curve and everything else if you do this right. So that's the first part. What you'll be given is a pointer to the head, right? And it's literally a linked list next and previous with some data. And you're going to sort that list, right? So in the unit test wise, it's going to, I create I create a list of 25,000 and then I search for a certain key. I give it to you. You just take that list and sort it. Then I'm going to verify that it's all sorted correctly. I'm also going to verify the next and previous on this as well. So making sure it's true. All right, so then the next one is merge. You kind of get the drill. I'm going to give you a linked list. And here is again 25,000. And you're going to call merge sort. And then the next one is combo. I give you a linked list. And I'm going to read your cutoff length. So when you're running this code here will be gone like this, we'll just use yours. And then when I test it, I add that line of code here, and whatever my test machine is, I'll put the correct number there. So then it always uses the right number. And it's just going to do the combo sort, and you pass in that cutoff length when to switch between the two kind of schemes, right? So that's the first half of this assignment. The next half of the assignment.
So, hey, So,
Yep.
so we manually run our code multiple times
To see
find-
it's to see that it's working, yeah. And you're gonna keep changing your numbers.
It's not a easy, obvious way to script that.
Knock yourself out if you want to. You can script it. But the catch here, you'll start to see the benefit, right? But the benefits, you know, it's on the small side because this is a further enhancement. So what you're going to get here is, you know, in release, you know, I was able to jump down here, which is about 300 times faster, just going from insertion to merge, which nothing special there. But then going from merge to a combo, I got another 20% faster. So you're not going to see a huge change, but it's still 20% faster just by tweaking a number is not bad. And the reason you have to kind of experimentally do it, if you want to write scripts, knock yourself out, is everybody's hardware is different. Everybody's platform is a little bit different. So you just can't use cold numbers and it will work. You have to kind of experiment to see where it really lies. Questions on this part? No.
And what's the grading criteria? It's just based on the speed up or?
Well, correctness and speed up.
Correct, okay.
Yeah, there's still, you know, unit tests and then speed up.
So is it ever worth keeping statistics about the list you're merging so that you know? I don't know whether to search it forward or backward or anything.
No,
like
no,
that.
you can't. You have to search them always forward.
Okay.
You know, the goal here isn't to try to beat, you know, have the best time. The goal is to use the technique and understand the technique, right?
Okay.
Because if you're looking for find a node, right? So think of the hot code list, right? If you keep a pointer to the tail, you'll get really fast numbers because you're not walking through all those nodes, right? So, you know, but that's against kind of what we're doing. We're understanding cache. In this case here, we're understanding how does algos and swapping between algos actually change performance.
Okay.
And also you get to refactor somebody else's code, which in itself is kind of fun in a completely painful way. All right, other questions on this first part here? All right, so this next part here is in the beginning of the quarter, I had to differentiate grad students and undergrad students. This is the section here. And what you're going to do, and it's much easier for me to kind of describe here, you're going to serialize your linked list. You can't use any helpers like, you know, STL, boost, proxy, you know, protocol buffers or anything like that. So you have to do it all by hand. So you're given a linked list, and what you're going to do is take that linked list and place it on a hard drive. So some file .bin. And then you're going to read that file. Oops. So you're going to read this file. And you're going to reconstruct the linked list. Right? These two linked lists have to be independent. Right? So this forces you to use the file system. You're going to take all this data here and you know, all this data and somehow place it into the file. Then you read this thing and reconstruct the linked list faithfully. Now, obviously, you know, there'll be pointers, right? Next and previous. These addresses will be different. This is this address 2, and this is address one, they're not equal to each other. They will be different addresses. There should be no cross wiring between these two. They're truly independent. So it's kind of like, if you think about it, it's kind of almost like a deep copy, right? We're going to take the linked list, put it into a file, turn around and read it back. So, you know, a lot of people have not had a lot of experience with files systems. So you're going to take this data and you're going to jam it into a buffer, right? And that buffer then gets written to the media, so your solid state or your actual spinning disk, whatever you have. So this is going to be written. And then you're going to turn around and you're going to read it into a buffer. And from there, you're going to turn around and create the linked list again. Right. And then when you're done using it, you free up your temporary. Right. So that's it on surface. It's pretty straightforward. Here's where the difference between undergrads and grads. Grad students, I mean undergrads, it just has to work, and you're allowed, you know, unlimited, you know, new and delete, right? And obviously you cannot leak. It's still, you know, you never can leak in this class, but you're allowed unlimited news and deletes. So I'll give you kind of a simple way to do this. A, B, C, D. you trying to think, do we know the size? Yeah. All right. So you know the count. Let's just say in this here, you know, the count is n equals 4, right? And you know you have access to a node, so you know the size of a node. So a quick and cheesy way to do it is size of node times the count gives you a buffer. Right. Then you're gonna turn around and read the data and then write the data. Then read the next data, write the next data. And you keep doing this until you fill it all in. Then then this gets written to the file system. Right. So that's your first part. This is the write.
And the nodes are all the same size?
Same size. Yeah, I'm being very nice. Right. So now this is again the undergrad. Right. And so now you have the file, right? And you're going to load the file into a buffer. Oops. Right. So load into the buffer. Then turn around, allocate a node, and then copy it over. And then here's your linked list. And then you're going to basically drag it and then add it to your linked list. Right. So that's one new. Then you allocate a buffer, copy the data over, drag it and add it to linked list. And you keep doing that until your list is over. You know, and this, you know, this is well formed. Right? When you finish creating the list, then you free the buffer. Right? Now, in this case here, we created 4 news. We actually created a new for this buffer. Right? Now, when we call delete on this, it has to go through and do 4 deletes. So you have to do the destructor to make sure it cleans up after itself. Right. The allocation wise, when we look at this, you're going to have 25,000 of these nodes. Right. So undergrads, you know, my expectation is 25,000, you know, plus, you know, 1, 2, 3 more, you know, these are all your news / deletes. Right. So any questions from the undergrads? You're going to read the linked list, write it over to a file. You're going to read that file and reconstruct the linked list. Right. Now the problem here is you're reading this file. Oh, I'm really nice. And I'll tell you that it's 25,000 of these. So you'll know exactly how to do it. So you read the file and you create this, right? So you're gonna have 25,000 plus a couple maybe supporting news for your buffers or something like that, right? So you gotta make sure everything's clean and deleted. Grad students. Right, so you are allowed 1 to 3 news, you know, deletes total. Same problem, right? So let's pretend we have the 4. Right. Right, so you know you have 4 of these, and you know the size of a node, right? So you know the size of the buffer. Boom. So you're going to start off here and, you know, copy this data in there. So boom, boom, boom. Right. And this data here is next, previous, you know, there's key and there's X and Y and Z, right? So that's kind of the node. So 100% of that is being recorded. Even the next, which is kind of silly, right? You know, key X, Y, right? So everything, full nodes get copied. Right. This is your buffer. Then you're going to write it to your media. Okay. Now you're going to read it. So you can start off with the media. Turn around and allocate your buffer. Right. And in here, I'm just going to, oops. right? So right. Here's your next. I was put next, but there's obviously previous. So, you know, right? And there's your X, Y, X, Y, X, Y, X, Y, right? So now your linked list, here's the, you know, O list, right? And here's your head pointer. It will point to this space. And then your next and previous will get point like this. And then the previous. Right? And that's it. So this is 1, 2, 3 news, deletes. And then you have to obviously do the destructor on this. And you do it that way. What this is going to save you is in the undergrad, they're going to do, you know, 25,000 news, right? In the grad, they're going to do 1 new or 1 or 2 or 3 news, right? And so that new is going to save you time. In the undergrad, we have to read the data and then copy it over to a thing. So there's a copy. So we get a cost for a new and we get a cost for the copy. In the grad version, we're doing a read from the disk. That's also the copy. And there's 1 new, 1 to 3 news. So there's 1 or 3 news, the copy. But what the grads have to do is go through this and fix those pointers. So they have to go through each pointer and correct it because it's wrong address.
So question. As the grad version, you really only, it seems that you can get by with exactly 2 news, 1 for the O list.
Absolutely. I'm just being generous with the 3.
Yeah. I mean, is there, at the risk of asking the question, can you do it with 1? I mean,
Oh yeah,
like,
you could do it with 1 only because of 1 reason. I tell you how many nodes. I tell you there's 25,000 nodes.
So you could.
But if I didn't tell you that, right? So I realized like I'm like, oh man, I made this thing a lot easier, right? So like, but if I was evil, right? Normally I am evil, but if I was evil, I would sit there and say, here's your data. Oh, by the way, good luck. You don't know how many nodes there are. This is an empty structure or an empty class, right? And all you get is 1 file. Now you need to actually add descriptions to it. So your data would also have, maybe on your file, you would have another here that tells you the number, the size, all that other stuff. And that would be your additional news.
So, I mean, couldn't you get away with basically doing a malloc of the number of nodes times the size of the node?
Absolutely, absolutely.
But also plus the size of the O list header, and that's your 1 thing.
Yeah, you can do that. Absolutely. I'm really letting you kind of decide how you want to do it. My only requirement is whatever messed up idea you have here, you make sure it works in the destructor. Right?
Got it.
So if you create 2 news, you better make sure that there's 2 releases in your destructor. If you do it with 1, there's 1. For the undergrads, if they, on their destructor, they're gonna have to do 25,000 new, deletes, right? 25K deletes. Right. So this is traditionally how it's done, is the undergrad approach, right? And this is a little bit simpler, but the grad approach isn't that much harder. We're just jamming it all into location and correcting the pointers after the fact. Now, on the assignment, on the PDF, it basically says grad or undergrad. Anybody can, grad students have to do grad. That I'm contractually tied. You have to do grad. But let's say you're an undergrad and you're like going, I want to do the grad way. Just write the word grad here. And you will be graded with that algorithm. If you are undergrad, I will grade with undergrad. So, some students have come to me like on, Ed, I really like the grad version. I like it better. That's faster. Can I do that as an undergrad? Absolutely. I'm not going to stop you from doing a slightly harder problem. But grad students have to do it. So when you see the PDF, it says grad or undergrad. So just type that in and that's it. I should have done a pull down if I was smart. I was an idiot. So you can do, undergrads can do either. Grads have to do it as maximum 3 allocations. Right. So that's the file system assignment. Now, I have lecture notes that are much more complicated to deal with variable sizes. So what if you had something like this? You had this, and this points to a different type of structure that's big. And then this points to a small structure. And also this points to this structure. So, these are all different ones. This is an A, this is a B, this is a C, and this is a D. And then this points to another C, right? And then you have something here, E, run out of colors. E has a pointer to 3 different guys, right? So what if I said, now take all this mess and put it into a file system? And you're only allowed 1 or 2 news. And that's what the lecture notes are. And I realize my lecture notes are more complicated than it's worth. And then it's worth. It's not a problem that you guys will see very frequently. So I wanted to first, before I completely confuse everybody, is to explain how do you do our assignment. And our assignment is, because they're all exactly the same size and shape, it makes it 1,000 times easier, right? So on the grad level, you copy this in, which is really simple. You literally just copy the whole thing over, right? So you copy all of the A object, the B object, C object, D object with the pointers over. Undergrads, when you're doing this, you have the option. You can just copy over the data, because you're going to be later putting it into a node, right? And then inserting it in there. And this node can then have the next and previous. And when you insert it, you can get it updated. Or you can choose to copy everything over. So this is, I think, one reason why some students want to do the grad version, because they think it's easier. Same, but we're going to copy the data over grad students are just gonna say, I'm copying the data plus the pointers over, right? And then when the grad students reconstruct it, they have to go rewrite these locations. So let's talk about that. So here's the buffer. And I'm just going to put two of these in here. So here is right. So here's the next. So you're going to have to write, if this is the address, right? This one next should point to this guy, right? So this is address plus size node gives you this address, right? So that goes into, and you're going to replace it. So here you're going to replace it with address plus size node, right? So that's the size node. I'm sorry, I did this to the wrong one. This will be over here, right? And then likewise, this becomes address plus 2 times the size of node, right? And the next one down here is address plus 3 times the size of node, right? You can kind of see, and then you can put this in a for loop and update all the nexus and update all the previouss.
Wait, are we allowed to use a for loop?
A for loop, yeah. You're reconstructing it.
I just assumed we'd have to do a while loop. Okay.
Well, in this case here, you know how many there are, right? I give you the number. I tell you it's 25,000. You know, so I'm giving you that. You can do a for loop, you can do while loop, whatever, it's up to you. But you have to update that. So that's kind of the trickery that you have to do, is from this step here, you have to overwrite those next locations with correct pointer because it's garbage right now. So you have to write it to the right location. But the win is, the reason why this is easy is that they're all exact same size. Right? So you're just rewriting the same pointer each time and just move down. So, you know. So because the nodes are, nodes are same size, this becomes an easier problem. And this kind of approaches the hot cold problem, right? The initialization part of it. So that's essentially it. If I gave you this one, some classes have 3 pointers, some have 1 pointer, some have different sizes. This makes it a lot harder. So our problem, because they're all exact same size linked lists, becomes very easy to do actually. And all you have to do is go through there and fix the pointers. Questions? So, so here's the right. So, you're gonna write, I'm gonna give you a list and you're gonna call write to function, and here's the name of the file. It has to be the same name file. So you would turn around and write, so give it a file name write. And what I did here in the code here is I kind of showed you a little bit of how do you open a file, write to a file and close a file. So you can kind of see a little bit. Obviously, you're gonna have to search and learn about open and fwrite if you haven't seen this before. Did you guys learn this in systems possibly?
Yes.
Good. Okay. I was just holding my breath. I'm like, oh my gosh, I hope the heck you learned that or seen it before. So you're just tweaking it out. If something bitches at you and wants the security, just put the _s, you know the drill. All right. On the reconstruction, here it is. I'm going to give you the count to make your life a lot nicer. And so here's the code. File and number of nodes. And I give you a little bit of sample code of how to open a file. We're going to open it for read binary. Then you're going to read it and then you're going to close it. When we're writing it, you're going to be writing it to binary. We don't want to read or write to text file because that is really slow. You don't want to write ASCII, you want to actually write binary. It makes it a lot faster. That's it. And it's pretty straightforward and pretty easy. And that. All right. So what I'm going to do now is show you the last part, which is the basics. The basics is about V tables. And I think this is important to go through. I have lecture notes here. But lecture notes are pretty easy. Like, what is a file system? How does it work? And the different issues. We'll go over this next week, but this has really no bearing on doing the assignment. This is more informational and kind of tweaking. And then I talk about that hellish linked list thing. So here's one. And so how do we actually do something that's arbitrary size and shape and more pointers? So you look at here, all these pointers are pointing to D, right? There's 2 out of K. There's, 2 out of this. There's, 1 out of C. So there's different sizes and shapes here going on. So I show you a generic way how to deal with that, but that's kind of beyond this assignment. And so I just want to hold off the formal lecture until next week. Okay, but I'll post it so you can look at it. But from the standpoint of getting this assignment done, you got everything right here. All right. The next assignment is this is, I think, a really useful assignment. This basics is V tables. So the V table assignment is there's no answers. It's a yes no kind of scenario. Let me show you one really quickly. So you're being given multiple questions. So let's look at number C. Here's C. So we look right here. Here's C's class, right? And we can go into C's class. There's C, and then there's D, right? There's a public inheritance. So the question is, here's C. Is there V tables in C? So we go to C. Is there V tables? Is there a V table of class? And you go, yeah, there's one. It is. So you just change this to 1. Okay, if there is, how many jump vectors are there? There's 2, right? Okay, what's the first jump vector? I go to C and like, it's this one here. Wait, I just go boom. Right. What's the second one? The second one is destructor. Right. Boom. And then the rest is there's no more. So you just put zeros. And I gave you a lot of extra ones in here. So there's a lot of zeros. Sorry about that, but. And that's it. And you go now to question D. For class D, is there a V table? You look at it, and you're like, okay. No, you know, or yes, and you just answer those questions. That's it. Right. But now let's talk about how do you really understand this and what is a V table and stuff like that. All right, so here's a class A, and I'm just going to give it a variable AX as an integer. And here is class B. And it has an integer variable BX, right? And first thing is, you know, this is UML notation. I hope to hell you've seen this before. If it's an open triangle pointing up, this is inheritance, right? The way to remember this is the parent, and this is the child, right? That should be in blue, right? And the way to always remember this, if you're at a family get together and there's a young kid and the kid gets scared, he's always pointing to his mom. Always points to his mom. He's reaching his arm out to his mom. That's the way to remember. Inheritance, the arrow doesn't go the other direction. It always points to the parent, right? All right, so let's talk about the data, right? When we instantiate this, remember these are ints. We sit there and say, I'm going to create an A object. So here's our A object. AX. So we go A star P equals new A, right? And so here's P points to this. Right? If I instantiate it as a B object, right? I'm going to use this terminology because it makes more sense to me. This object is born a B object, right? So now we're going to be P object. How is this constructed? Well, it's constructed is it constructs going down. So it constructs A, then B. So what we get is this. Here's the A, and here's the B. And I don't know if you can see this, but there's two boxes. So the PB pointer points at the top of the box. The PA pointer points just to the red box. And this is why polymorphism works. You can pass a B object into an A input because they're actually the same pointer, right? So if you did this, if you said there's a B right, and we know PB points to the first location, but also PA points to the first location, but it only covers red. The blue covers all of the blue, which also encompasses the red. So if we have a function here, function that takes in an A object, right? We're allowed to do this, foo PB, right? The reason why, you know, this is the signature, this is the calling function. The reason why we can do this is we're looking for an A pointer. It's the same location. It's still an A. And this is why polymorphism works. Do you guys, was polymorphism introduced in data structures? Anybody? Yep, okay. All right. Now, let's talk about the constructors. The constructors. Right. So the simple and dirty is it's constructed like a stack. The construction starts from the top and goes down. The destruction starts from the bottom and goes to the top. Right? Now, no matter how complicated our data structures may be, right? And so right? So let's say we had this crazy inheritance structure, right? When something is born, it's literally, let's say C, it's C, and you go all the way up until you hit the top, and that's your stack, A, B, and C. If you have E, it's just E to A. E and A is only on your stack. If you have H, you get H all the way to A, so you get A, F, G, and H, right? If you break some of these, if you can sit there and start from the middle of it. So B, I'm just instantiating B, you get B and A on the stack. So whenever something is created, it goes from the wherever the node is, and it keeps moving all the way up until it hits the top parent node. So here's these classes, right? And we create B, and we say B, we'll say 5, 7, right? So we're going to instantiate B. Well, this goes into a special constructor here, and it takes in X and then Y. And then here's a constructor over here, A, that takes in X, right? So how this works is, here's 2 arguments. We're supposed to, let me make sure it's very obvious. This is the Y component, and X is the A component. How this works is, I said the construction works from top down. You call this, and it just jumps in here. And the very first thing it does, it goes into the initializer list, right? If you specify this, you can say, hey, I want to use A X, comma, B, Y, Y, right? This first term here is which guy to call on the A level. If you don't put anything there, it still jumps instantly to A and fires off A. So A is the first one that gets called. It jumps into the B function to say, hey, which A to call? It goes here, it goes, nobody's defined anything, so go to default. So it would call the default constructor. If I delegate X over, I can sit there and say, you know what? Pass the X here. And it goes, okay, cool. It will call this guy. It does the work. Then when it comes down, it then calls the next argument in the list. Right? So initializer list tells you which one to call. So that's how we can guarantee that an A class is called before the B class. So the construction is always from the top, goes all the way down to the bottom. Right? When you call the destructor, so let's pretend this is dynamic. Right? And I go delete PB, it's always going to fire off the B destructor first. Then it's going to, remember, I'm sorry, this should be pink because it's red, right? Then it's going to go up a level and fire off the A's destructor. Keep moving up here. starts here and then goes up. Right? There's no overloading of destructors. You only get one. That's it. It's defaulted. The reason for that, if you want to get kind of technical, because when you call a destructor, you don't pass in parameters. You don't pass in parameters on the destructor. So there's no way to discriminate this to tell you which destructor to call, since you don't pass anything. Therefore, there's only one is defaulted. Okay. So now here's our problem. Our A destructor does nothing. Right? Our B's destructor delete P. So in here we have a P that we call new integer. Place the code over here. B's constructor has P equals new int, right? And then here's A's constructor, X equals 5. Right. So let's kind of do a scenario here. So we do it as a B object. B is born. Right. Well, so what does that mean? That means we fire off. Remember, we fire off the A, and then we go down, and then we fire off B. So A is right here, AX, and it's 5. Then we get down to the B. There's a pointer that points to some glob of data. There's your PB, right? And PB. Right. Now we go delete PB, right? And it goes destructor, sort of frees this up. Then it goes nothing. And then this thing gets released. Okay, everything's kind of cool. All right, same problem, exactly the same. Nothing's changed. But we're going to do it this way. I'll do down here. It's easier. New B, right? So here it is. AX. Then it fires off B. P points to some glob. Right? So that's the new. But we're going to say it equals A object. Like what? What happened there? This is called compile time polymorphism. Right? Because remember, B is also an A pointer. We're going to do it on construction. We're going to just do it right there on construction. Right? So we have this PA points to the top. Right? So now we go delete PA, right? What gets called? What gets called? PA is an A pointer. So it calls this. That's the parent. There's nothing more to go up, so it stops. And guess what just happened? Anybody can take a guess what just happened?
Leaked memory for the size of,
Yeah, we just leaked the P memory, right? This is why we have a virtual function. This is why we have a virtual function, right? This is a problem. And this happens more frequently than we know, right? So what we do now is this. Everything's the same, but we put a virtual function, a virtual A destructor. Still does nothing. And here's your P. And now here's your B's destructor. Right. So we do the same thing again. We say, okay, A star PA equals new B. So now we get here's our A. Here's our P. Right. And P points to gobbledygook. Right. But because we have this keyword virtual, it's going to add a virtual pointer to it. So instead of this, it's going to add here. Virtual pointer. Right. So what does this virtual pointer do? It points to a table. I'm going to scoot everybody over. All right. Right. And this V table points to a table. This is a virtual table. Right. And what we get from there is this is the list of functions that are virtual. So in here, it'll be the destructor, right? A. And this is going to be mapped to the destructor of B. Okay. So what happens now is when we go delete PA, it jumps over, here's PA. It goes, oh, I got a V table. Jump to the V table. I'm about to call A's destructor. It goes, redirect me to B's destructor. It goes, call that one first. So it calls this one, then it calls up and calls that one. So the V table is here for one key word, right? Is how was this born? Who created this? Why was it created? What's the shape of it created? Did it have 4 arms? Did it, does it have a sports car connected to it? Whatever it was connected, the V table is that is that is it's the original connection. Then no matter how you do your casting later, it knows to call the right one on the destruction. Right. So couple rules with the V tables. If you have a class A and you have data and you have some methods, right? No V table, right? Soon as I add one virtual function, now I have a V table. If I add here 3 functions, 1 table. So basically, if there's 1, you get 1. If you have 10, you still get 1. If you get 30, you still get 1. But if there's none, then there's no V table. Class A.
Is the V table part of the size of?
Yes.
Of the object?
Yes. Okay, so here's your class A, and there's foo, and then there's X, right? But then you derive from it class B, virtual function foo, Y. If we instantiate just A, no V table. Soon as we instantiate B, we get A with it, V table, right? So remember, we have this. So if we instantiate A only, no V table. As soon as we add B, we also bought A. Now A has a V table. Right? The V table always lives at the top. Well, actually, I take that back. It can live anywhere. The convention is it's not a hard spec. It tends to live on the top. Strastrup got a long diatribe about why, it should be on the top because you have the verbal length and stuff like that. So we always notice it first, right? The V table, if one exists, it will point to a table. This table will have as many unique V functions as it needs. The V table is 4 bytes. So if just kind of go here, if we had a vector, right, inside the vector class, we need it to be a line 128, right? And so we do our union trick, and here's our data. X, Y, Z, W. And if somebody later goes, you know what? That should have a default constructor. Oops. Like, thanks, buddy. Now you just added a V pointer, which goes to the table. And now our alignment's not aligned anymore. So as soon as you add a V pointer, you bought 4 bytes and everything is 4 bytes lower than that. If you had a double, D is your class, right? Double is 8 bytes. So this is now D, and this is aligned to 8. somebody adds that virtual function, right? It adds a v pointer, right? Problem is this needs to be 8, so then it adds pad to guarantee that that's 8. Oh, women, let me take this back. We should do an experiment to see if that's true. I thought I knew it, but now I'm questioning myself. So we have to check this. So this be a check. Right. The reason why I think it's a check because they don't honor the vector. I know the vector gets knocked out, so this probably isn't honored as well. So it can get us in trouble. All right. So let me show you kind of how it works in C++ land. This is kind of cool in a geeky way. So let's do number D. Or I guess we start with C. C. All right, C. We look at C's class and we go, I see a virtual function. So by my definition, I see 2 virtual functions. So by my definition, if C has a virtual class, it should have a virtual, it has 1 virtual method or more, it has a virtual table, right? So let's check that. C star PC, PC equals new C, right? Cool. And then you're like, okay, let's look at this variable. So I'll do add a watch window. There's PC. I open it up. It says, hey, there's a V pointer. Like, thanks. This is the easiest assignment on earth, right? Do not trust this. Microsoft gets this wrong. Microsoft gets this wrong. But it has a V table, right? And what's in the V table? 2 methods, method for weight, methods for the destructor. And we look at here, here's weight. And then you'll see here, it's a destructor. This is a single destructor. We use delete, not delete array. So that you'll see this thing here. Sometimes you'll see the term vector deleting or scalar deleting. You know, this is a destructor, okay? All right, so now let's take a look at this and see, can we look at this in a better, cooler way, right? So we're here, what we're gonna do is open up. You have to wait till it runs, open up in debug, window, memory. Poop, right? Then we're gonna open up another one, debug, window, memory, memory 2, boop. And we'll drag it over here and put it to the bottom there. All right. Now we take PC and put it in the first window. PC. Boom. And now we're going to right click on this. And you want these to be 4 bytes. There it is. And then this should be 4 bytes. Let's see if I can expand this a little more for you. Can you guys see this, or do I need to expand it?
I can see it.
I can see it.
Why 4 bytes? Is that because that's the size of a pointer, or because that's
Yeah,
the
size of a pointer. That's all. I'm just doing it just for making it easier. Nope, that wasn't it. One more try. I need it a little bigger. So if you were a memory window, what would you be called? Dog. All right, I'm not sure where we call. All right, so it stays. All right, so here, and then PC. Wow, I really need. I need to. Sorry, I need to expand this. See if it takes a reboot or not. There you go. All right. All right. Didn't get any better. Sorry about that. All right. So here's PC. Boom. All right. And we put this into 4-byte mode. It's 4-byte mode, right? Man, do I really need that thing bigger? All right. So so here's our data, right? Our data here in C, let's go back to C, is we're initializing a 5 and 6, and we can see here it says 5 and 6. And the beginning of PC, right? PC, it points to F8, F8. So this one right here is the V table. So we just cut and paste and place it here, and we add the 0x in front of it. Boom. There's our V table. So here's 2 entries. Crap.
You got 0C, not 0X there.
Oh, thank you. Thank you. Okay, cool. All right, we have 2 entries. 2 entries, and it's null terminated. So there's 2 entries. So now we take the first one, ready? Copy this, open, convert to disassembly. So we click on the source file and let's go disassemble, boom. And then up here, we type in this, and again, we add the 0x in front of it. Boom, this is the line. Our jump table, our V table goes to C weight. Then the next one, goes right here to scalar deleting destructor. Right, here we go. And the first one was weight. So Microsoft is right here. The second one, Microsoft is wrong. The second one is a scalar deleting, and they have it as a vector deleting destructor, right? And you're like, on, well, wait a minute, what the hell? What's the difference between the two, right? So if you make a right, this is an array, so you have to call delete bracket p, right? This right here is a vector destructor, right? If you did P. This one here is a scalar destructor. So we really should be pointing to a scalar destructor. So this is just an example that this little window here is sometimes wrong. And sometimes really wrong, like it has 2 entries, there should be 3, or it points to the wrong thing. This is Microsoft, gave it to some junior programmer and they screwed it up, right? But what's true is not the watch window. What's true is the data. So this data will never lie. This is your V pointer at the top. It jumps to a V table. The V table in this case has 2 addresses, and you look at the address, and this is something to see where it really points to. And that kind of gives you an idea of how V tables work. So you can have, in your base class A, you can have a virtual function weight. And let's say it returns 5, right? And then in your derived class, you can have virtual function weight returns 10. Then you have you create this object B star P B new B. So it's born a B object, right? Then somewhere downstream, you go, you know what? I have an A pointer, and I'm going to sit there and just set it so it does the casting there. And then you go P arrow weight. It's going to call, even though it's an A object, you think you're calling that guy, but because it has a V table, it goes to how was this thing created, right? It was created a B object, and the B object said, hey, you're supposed to use this function for weight. And so it's going to jump in the jump table and jump here and call and return 10. And this is how abstract methods work, virtual methods work, virtual destructors, all this stuff works. Is how is the class initially constructed or born, and then how is it, no matter how it's used, it's going to, virtual functions will honor the way it was initially created. It was initially created saying, you know what, I want you to call this weight. No matter what kind of casting you do, it will call this weight because it was initially created that way. If you don't have the virtual function in there, there's no vtable pointer, then in this case here, then in this case here, it will call A because it says I'm an A pointer. So the V pointer is very, very important when you're dealing with inheritance. And how it works is it just appends one pointer to the top.
So does the virtual table have only a pointer to the B class weight if it was created as a B, or does it have both of them in there?
No, just B.
Oh, it finds B first.
It just says I was created as a B object. What functions are correct for a B object? That's it.
So I mean, you're making a metaphor when it says I know I was a B object.
No, it doesn't know. It doesn't know that at all. It keeps
Right.
the table. It keeps the table of functions to override.
Okay.
But it's really, you're right. I did make the metaphor, but if you use that metaphor, you get it correct in your head.
Right.
Right. So it was created as a B object. These are the pointers and the methods that B expects. So when you cast it to an A or some other thing, it will still honor the way it was initially created. So why is V virtual functions so damn useful, right? Is that if you have an A class, right, and you have a thing saying, you know, let's put this right. How many bytes am I? You know, right here, it has X and it says, it'll say virtual function size, right? Let's say you had a function here and you go, I return 4. I'm 4 bytes, right? And then this one here has Y and Z, and its size says the size of the whole thing here is 12, because I have these 2 variables plus X, right? So it returns 12. B. And you're a good citizen, right? So you say, hey, I'm creating a B object, it's a B object, damn it, right? And so you're a good citizen, and you play by the rules, right? But somewhere downstream, there's this function here, it says report. And it says I take an A pointer, right? That's a report. And you're like, okay. And I go, I'll do that report. And you pass in a PB, which then treats it like an A. But inside of here, it goes, you know what? Get the size, right? And print the size on the screen, right? So print the size on the screen. It goes here, I was created a B object, my size is 12. My report says, hey, I'm polymorphically, I'm only an A. But the report goes, what's the size? And it goes, no, use this size, use 12. And this is where it saves your bacon, right? This is where it totally saves you, because it's like going, I'm very good. I was playing by the rules. I created a B object. I'm using it as a B pointer. And this function is polymorphically, and then also I get a surprise. And if you did the virtual function, it works. And if you didn't do the virtual, you got the wrong answer. So this virtual function really allows you to override methods proportional to your inheritance. And it preserves it. Now, to me, the most compelling reason for a virtual table by far is the memory leak. Is this one. Because this is so easy to inadvertently delete the wrong pointer in your leaking memory. So that's a big reason why I like it. So if you read effective C++, this kind of rules of the road. This is by Myers. The guy with the crazy hair. He actually makes an argument that says, if your class is ever going to be used in an inheritance structure, just always use a virtual destructor. Just always do it. Because this way, if it polymorphically gets casted, you don't leak memory. And I would say that's like 99% of the time correct. Times I go against that when I'm doing abstract data types like a vector. Because if I put a virtual function on there, it just knocks out my alignment. So that's the V table kind of discussion, and a little bit more of the internals, how it really works. Questions? All right. So I'm going to make a couple tweaks on the homework and I'll release it tomorrow morning. And expect a lot of grading to be kind of landing in your inbox this weekend. So the PA6, I mean 7, no 6, SIMD will be graded with the because I can tell a lot of people are really far behind. You're not going to finish this by Saturday. I will grade PA6 with PA7 at the same time. So this way it gives you a little more slop time on there. So, please, please, please keep crunching, stay with it. You're almost there. Next week is particles. Next week we start particle optimization. So, so it'd be really nice to kind of get your PAs out of the way so you're ready to work on the particle system. Okay. Thanks, everybody. I'm going to stop this recording and then I'm going to open it back up. If you want to do any extended office hours, I'm more than willing to help out. Okay. And thanks for coming online, everybody. And I'm not sure what's going to happen next week. It all depends on complications and issues with my mom. But we might have to do this one more week. My gut says it's probably 2 weeks. But I will let you know as soon as I know. So thank you for accommodating. Thank you. All right. Good night.
Thank you.
Thank you, Professor. Good night.
Thanks.
Good night, everyone.